In this example problem, we're going to find probability based upon the relationship between how far a certain point that you're looking for in the data would be from the data's average, and that is measured in stats terms as a standard deviation. So for the purpose of this problem, we are going to be looking at a sample of 30 children, and these 30 children are going to begin putting words together into sentences at a mean average age of 20.7 months, and the standard deviation of these 30 children sampled was 1.95. So, in other terms, about two-thirds of these children started forming sentences somewhere within 1.95 months below the average and 1.95 months above the average. To figure out the probability of this, we need to figure out how far any one given point would be from that 20.7 month average for when children start putting sentences together. So the formula we're going to use for that is x minus x bar, or the point we're looking for minus the average of the sample, divided by the sample standard deviation. That's going to give us how many standard deviations away from average that data point lies, or if you will, the z-score. So let's start with the first one. We're looking for the z-score that determines the probability that child will begin to combine words before the age of 26 months. Well, that means our z, or x, excuse me, is 26. We know from the data given in here that the average of the sample was 20.7. So this would be well past average. According to our sample, most children begin to put sentences together at 20.7 months. For a child to not start doing so until 26 months would be well after what is typical. And I know this because this sample has a standard deviation of 1.95. So if I take, and it's very important you put the first two inputs into parentheses, 26 minus 20.7, and close that parenthesis and divide by 1.95, we're going to come up with 2.72. For a child to not start speaking in sentences until they were 26 months old is 2.72 standard deviations above mean. From our normal distribution here, that's very, very far above mean. There's very few spots in the data that you'll get that are that far above the sample mean of 20.7. But saying it in standard deviation is one thing, let's put it into a probability. And to do so, we have these reference tables, and your homework this week has these reference tables provided. How you use them is the left column is the whole number place and the tens place. So we have 2.72. We'd have to find 2.7 in here. And then the headers on the columns are the hundreds place. So what I need to do to find 2.72 is go down to 2.7 and then go over to 0.2, and that's 0.9967. So the P that X is less than 26 months is 0.9967. And what that means, interpreted into regular language, is that 99.67% of children will start speaking in sentences before they're 26 months old. So that's the way you can do it in a formula, but we are using Excel here, and Excel can shortcut it using the norm.dist function. So in this case, norm.dist, or normal distribution, if you will ask you for four inputs. The first one is the x, and the x we know to be 26. The second thing it asks you for is the mean, and we know the mean of the sample is 20.7. The third thing it asks you for is the standard deviation of the sample. We know that to be 1.95. And then the last thing it asks you is this a cumulative distribution or a probability mass function? The latter, not covered in this course at this point in time. As you can tell from the header on this table, we are using cumulative normal distributions. So we do want to put in the input that tells it this is cumulative distribution, which means that'll be true. And then close that, and as you can see, we get the same number up here. So just a way to shortcut it. This is the long form way for using Excel. Knowing what you need to look for, the norm.dist function gives you the probability. And we can move on to event two, and in this case, determine the z-score that will determine the probability that a child will begin to combine words at some age after 25 months. And the after is what is incredibly, I'll make it bold right here, important in this question. The probabilities listed in this table are the probability of something below that point. So that's why I just left 0.9967 up here because it was before or below the age. Well, this doesn't list the probability of something happening after. If I can go through and find the z-score, the number that I'm going to return isn't going to be the probability of a child beginning to form sentences after 25 months. It's going to be the probability of a child beginning to form sentences before 25 months. But we can change that around. So let's first find our z-score. And in this case, 25 is going to be our x. The x bar is still this 20.7 that we used before. The sample standard deviation is still 1.95. So for z, it equals, in parentheses, your x minus your x bar, close the parenthesis, divided by your sample standard deviation, or your s, and we get 2.21. So a child beginning to speak in sentences at 25 months would be 2.21 standard deviations above mean. Well, I can go through right here and find the 2.21 probability. So 2.2 is right here. Going over 2.1 is 0.9864. That's the probability of a child beginning to speak in sentences before 25 months, 98.64% chance. But we don't want that. We want above. Well, these two outcomes are mutually exclusive. You either start speaking in sentences before 25 months or you have to start speaking after 25 months. And if this is the probability of before, the probability of after has to be the complement of that. In this case, if you have a 98.64% chance of speaking in sentences before 25 months, you would have a 1.36% chance, the complement of that, was speaking after. So for an after question, instead of just using the number that gets pulled from the table, you use 1 minus this number. So this is going to equal 1 minus 0.9864. And that comes out to 0.0136. So there's a very small chance that it's going to take at least 25 months for any one given child to start speaking in sentences. And we can use the norm.dist function here as well, if you wanted to, applying that same concept. Norm.dist, just like the numbers on this table, always gives you the probability of an event occurring below, before, whatever term you have the situation. We want the complement of that. So instead of just using norm.dist, I'm going to do the same thing that I did up here. This is equal to 1 minus norm.dist. The x that we're looking for now is 25. The mean of the sample is 20.7. The standard deviation of the sample is 1.95. And we want to say true. And you'll get 0.0137. So why the difference between these two numbers? Yes, they're very close, but one is 1/1000th off of the other. The reason being is this chart rounds to the nearest hundreds place. So we had 2.21 here. Well, our z, if I increase the decimal, isn't actually 2.21. It's 2.20 and a whole bunch of things afterwards. And there are individual numbers that lie in between the gap. But if they put in, every spot to the millionths place, this table would be absolutely massive, and no one wants that. So it's my long form way of saying that if you get a number using the norm.dist function that is slightly different than the option that you would get from using the chart method, you didn't do anything wrong. It's just because the chart rounds the nearest hundredth and the norm.dist function takes into consideration every single decimal place that you had in your z-score. Moving on to event number 3 over here. And in event number 3, we're looking for a between. And that's the important term in this case. If you get a question that's asking you to find the probability that something is going to exist within a certain range, what you need to do is find the z-score for each of the bounds of your range, if you will, the lower number and the higher number. Find the probabilities associated with those z-score and find the difference between the probabilities associated with those z-scores. So we're looking for the probability that a child doesn't begin to combine words, speak in sentences, until they're at some point between 22 and 24 months old. So let's use 22 and 24 as our two values of x. I like to start with the bigger one because I'm going to subtract this at the end. So the first one I'm going to do is 24 minus 20.7, our sample mean, divided by 1.95, our sample standard deviation. This equals 24 minus 20.7 divided by 1.95, and that comes out to be 1.69. Let's do it for the other bound. The other bound was 22 months. So 22 is our x this time. 20.7 is still our sample average. 1.95 is still our sample standard deviation, and our z is going to equal, in parentheses, 22 minus 20.7, close that parenthesis, divided by 1.95, and it is 0.67. So what I need to do is I need to go and I need to find the probabilities that are associated with these two z-scores. I made this a table so we could drag it down. I might have to zoom out a little bit so we can see a little better though. There we go. So coming down here, these are the two z-scores that we're looking for. The z-score for, I think I'm going to get there. Yep, 1.69. 1.6 is right here. We go over to 9, and 9 is 0.9545. So that would be the probability of somebody beginning to form sentences in less than 24 months, so 0.9545. Let's find the p for the other z-score that we're given, which is 0.67. So 0.6, roll on over until we find the intersection with 0.07 on the top, and it's 0.7486. So that is our probability of speaking in less than 22 months. And then this probability accounts for everything below 24 months, which means it would include everything from 1 month all the way up to 24. This is the probability below 22 months, which includes 1 to 22. So both of these probabilities include the range of 1 month. If somebody magically started speaking in sentences the moment they were born would be impressive, but it includes the same range of 1 month all the way up to 22 months in both of them. We don't want that. We just want the spot that this contains that this doesn't contain. In this case, the probability of being greater than 22 months, but less than 24 months. And that's what this little range down here says. And how you find that? Incredibly simple. You just find the difference between the two numbers. 0.9545 minus 0.7486 equals 0.2059. So about 20.5% of all children don't start forming sentences until they're somewhere between 22 and 24 months. And just to be thorough, you can do this with the norm.dist function, adhering to this philosophy that you need to find the probability of the higher number, your upper bound, using the norm.dist function, and the probability of finding your lower bound using the norm.dist function. And the difference between those two is the probability of a data point existing within that range. So this equals norm.dist. Open your parenthesis. The first x you have is the upper bound, and that was 24. The mean of the sample is 20.7. Standard deviation of the sample is 1.95, and cumulative is true. Minus norm.dist. And this time we're going to use the lower bound, which was 22, and all the other inputs are the same, 20.7 for the mean, 1.95 for the standard deviation, and this is cumulative distribution, so we'll put true in one more time. And as you see, we get 0.2072. Again, it is slightly different, but very close to this number, and the reason for the difference is because this rounds off while the norm.dist function will not, but the answer is still essentially the same. So when you're asked to find a probability by determining z-scores, the big thing is you're going to ask from the get-go is it a less than below question, or is it an above greater than question, or is it a between question? Because that dictates procedure that you need to use. If it's a less than question, just take the number off of your z table or the number given by the norm.dist function, and it's your answer. If you're looking for an after, greater than, above question, anything that's higher than a certain point, it is 1 minus the number that you get from the table, or 1 minus the return that you get from the norm.dist function. And if you're looking for a probability in a range, a probability of a figure being between two different numbers, you find the two probabilities associated with the z-scores for the upper bounds, and the two probabilities from your norm.dist function. And then you just take the difference of those two numbers, and that is your probability.